Hi folks, welcome to the Trig Review. This is just a little review that I made for my students in PEI Canada before the Math SL exams. It's not an exhaustive list of the different sections and problem types, just some of the key concepts. If you want to make the most of this presentation, I recommend that you actually download the notes at the link below. You can do the work in advance and then work through the presentation and check your work. There are often a lot of different ways to solve a particular problem. If you have a different way that you've been taught, by all means, please do that. Okay, we'll start with triangle trigonometry. First of all, right-angle triangle trigonometry. So you need to know SOHCAHTOA, which is just a little mnemonic device for sine of an angle is opposite over hypotenuse, cosine's adjacent over hypotenuse, tangents opposite over adjacent, in right-angle triangle only. You should also know Pythagorean theorem, which hopefully everybody does very well by this point. I need to know different values of sine, cosine, and tangent, and you should know them at least for the following angles, 0 through 90. In terms of degrees, so in radian measured, 0 would still be 0. 30 degrees is pi over 6 radians, 45 is pi over 4, 60 degrees is pi over 3 radians, and 90 degrees is pi over 2 radians, because pi radians is the same as 180 degrees. Okay, in terms of sine of theta, a sine of 0 is 0, or the square root of 0 over 2. The next one is going to be the square root of 1 over 2, or just 1 over 2. Next one, square root of 2 over 2, then square root of 3 over 2, then square root of 4 over 2, which is probably more easily written as the number 1. So there's a little trick for being able to write them out. For cosine, we just go in the opposite order. Goes from 1, and then root 3 over 2, root 2 over 2, root 1 over 2, which is just 1 over 2, and root 0 over 2, which is just 0. Tangent is sine over cosine. Okay, and I've got my sine and cosine values up top, so 0 divided by 1 is just 0. A half divided by root 3 over 2. If you rationalize the denominator, it's root 3 over 3. If you don't, it's just 1 over root 3. Next one is 1. Next one is root 3. And finally, we'd have 1 divided by 0. And we know we can't divide by 0, so that's undefined. Trigonometry that deals with non-right triangles or oblique triangles. So you've got sine law and cosine law. Sine law you're going to use when you know a pair, which means a side and its opposite angle. You can write it in different formats. Here we have an ideal way for finding sides, just because it's got the side on top. Here, ideal for finding angles, we put the angle on top. Okay, and this is also equal to side C over sine of angle C. I only wrote 2 of those pairs, because typically when you set it up in a problem, you're only going to use 2 pairs. Remember that when you use sine law to find an angle, you might end up with the ambiguous case, so you need to consider both an acute and an obtuse solution for your angle, and then just see if both of those are actually valid. Your GDC is only going to give you the acute solution. Cosine law, it's great for finding a third side when you know 2 sides and the included angle. So if I knew this was, 3, 2, and I had an angle here of 100 degrees, cosine law lets me find this side over here, the C. If you want to find sides, this is the ideal setup. Or it can be rearranged for finding angles when you know 3 sides. Okay, those are given in your formula booklet. Let's put some of this to use, but before we do that, we'll take a look at a couple of other little applications. Lines in 2D. If you've got a line that passes through the x-axis and forms some angle with the positive x-axis, its slope is given by the tangent of whatever that angle is. So here, I've got 30 degrees. That's the angle that this line is making with the positive x-axis. So the slope of that line is just tan of 30 degrees, which we know is root 3 over 3. Okay, just a little shortcut. You could have also set it up using slope and setting up a triangle. Triangle area. Okay, this is our standard formula. if you happen to know the height of the triangle, or if you have a right angle triangle, that automatically gives you the height. And then the general form is right here. Let's put that to use in this triangle. Here we really do have two sides and the included angle, and that's important. Where it says half AB sine C, the angle has to be between the two known sides. Okay, so that's a half, 7 times 12 times sine 120 degrees. Let's put this in our GDC. So we've got 0.5 times 7 times 12 times the sine of 120. Make sure that I'm in degree mode. And we get 36.4 square centimeters. All right. Or we could have done this exactly. A equals a half times 7 times 12 times the sine of 120. Okay, the sine of 120 is going to be the same as the sine of 60 degrees because it just ends up on the opposite side of the y-axis. It's got the same y value, or the same height. So this is going to be a half times 7 times 12 times square root of 3 over 2. So in exact terms, that would give us 21 root 3 centimeters squared. You'd want to be aware of a few properties involving circles, chords, tangents, sector areas, and segments. So here are a few little diagrams. If you've got a circle with the center, O, and you've got a chord, this is called the perpendicular bisector theorem. If some line segment goes through the center and forms a perpendicular angle with some chord, it automatically bisects that chord, so puts it into two equal parts, and we'd be looking at equal radii, of course, on the other side. So you end up with two identical triangles. Points of contact between tangents and radii. So if you've got a radius that meets a tangent, they automatically form a right angle. Okay? And that gives rise to this property. We've got radius and a tangent form a right angle. Okay? And you can have the identical thing happening on the other side. So where tangents meet, we end up with these two identical triangles, identical angles here, identical angles over here. Okay, and of course there's a shared side. So for the next little bit, I'm not going to really harp on the algebra of it. I think that you can probably work these out fairly easily. So if you want to go through this, just pause, work it through, and then check it out. For number one, we want to find the unknown, this x angle down here. So I can split this into a triangle like this. Okay, I know I've got a radius and a tangent. They're meeting at a right angle. So I can say, I know this is 6 centimeters and 10 centimeters. I could call this little angle in here y, and I know the opposite and the adjacent. So y is going to be the inverse tangent, or arctan, of 6 over 10, or 0.6. Gives me that y is 30.96 degrees in my GDC. And now I just double that for my x, because I'd have two identical triangles. So double it, that'll give us the full angle, which is 61.9 degrees. Next one requires a little bit of creative thought. Figure we've got AB is 1 centimeter right here. AC is 3 centimeters. Find the radius of the circle. All right, so here I could draw in a radius r. Then I'd have this triangle where this blue side from O to A is just going to be 1 less than r, because AB is r. AB is 1, rather. And this final side, that's 3. So I can set up with Pythagorean theorem, r squared equals r minus 1 all squared plus 3 squared. If I solve that, I'll get r is 5. Now we want the angle subtended by the chord at the center of the circle. So now that we know this, we've got this triangle that has a length of AC, from AC of 3. And we know that we've got 5 for our radius of the circle. Okay, and I want to find this angle in here. I know opposite. I know hypotenuse. So theta is just going to be the inverse sine, or arc sine, of 3 over 5, which will give us 36.9 degrees. Or we could work in radians. Sectors. I've given the formulas here in terms of degrees, but they're given in terms of radians in your formula booklet. We should be able to work with them either way. Okay, should be pretty straightforward. All of our formulas for, say, triangle area work in radians as well. It's just that a triangle, instead of adding up to 180 degrees, would add up to pi radians. They mean the same thing. Find the area of the triangle OAB. Okay, well, what do we know here? We don't really know enough. What I meant to put on here is that we've got 12 centimeters for our radius. Okay, so now it's pretty straightforward. This is just going to be a half times 12 times 12 times the sine of 110. Okay, just setting it up with your area formula. Pretty straightforward. 67.7 units squared. Again, if you want to do this so that you're making sure your work is good, you might want to pause and then just check. The area of the shaded sector OAB. Or sorry, not the shaded sector, but the sector OAB. So sector area comes from theta over 360. It's 110 over 360. Times pi times r squared. Okay, that gives us 138.2 units squared. The area of the shaded segment. So the shaded segment is just the whole sector area minus the area of the triangle. So for part C, that's all we'd need to do. Our 138.2 minus our 67.7 would give us 70.5 units squared. Now, if you'd kept more sig figs, you'd actually end up with 70.6. We won't worry about that too much, though. All right, this is sort of your basic trigonometric applications here for triangles. So we've got 3 sides in this first triangle, and we want to find an angle. This is an ideal case for cosine law. And we really want to have the arrangement that has cos x out front. So it's the 2 sides that are next to the angle you're interested in that you're going to add their squares and subtract the square of the opposite side. Okay, all over 2 by the sides that it touches. Work that out and then do inverse cosine. You're going to get 44.4 degrees. All right, the next one. You might be asking yourself, do I use cosine law or sine law here? Well, since you don't know a pair, you don't know an angle and its opposite side, we're going to be looking at cosine law. You can also tell that we're using cosine law because we've got 2 sides and the included angle, the angle between them. So x squared is going to be 10 squared plus 7 squared minus 2 by 10 by 7 by cos 45. We could actually do this exactly, but if you do it in your GDC, you're going to get x squared is about 50, and x is the square root of 50, or about 7.07. Okay, and exactly it'll be root 50, or 5 root 2. Last one. Here we do actually know a pair. So I'm going to set this up So that my unknowns on top, okay, sine of x divided by 21, its opposite side, equals sine 23 over its opposite side. Isolate sine x. Find the inverse sine, or arcsine, of that, and we get x equals 43.1 from our GDC. Here's where you have to be really careful. We've found a solution for an angle using sine law. There could be two solutions, though. Our GDC said it was 43.1, or it could be 180 minus that 43.1 from ambiguous case, which would be to 3 sig figs 137 degrees. And really, in this case, the diagram suggests the 137 degrees. Okay, radian measure. You should know that your calculator is going to default to radian measure. So when you're doing at the start of your exam, you're resetting your calculator memory. Now you're in radians. Pi radians is 180 degrees. Your basic graphs, these are periodic graphs, so they continue on forever in both directions. But you should know some properties about them. A full cycle of your basic sine graph, if we, quote, start at 0, then a full cycle is going to take 2 pi units on the x-axis, which would correspond to 360 degrees, or a full revolution on your unit circle. Cos x, same thing. It starts high, but it takes 2 pi units to do a full cycle. These are the basic graphs, and again, they keep on going forever in both directions. Properties you should know. First of all, amplitude on your basic graph is 1. It's half the vertical distance traveled by the graph. So this goes from a max of 1 down to a min of negative 1. This one, max of 1, min of negative 1. The principal axis is the x-axis on your basic graph. That means the horizontal line that the middle of your sine graph or cosine graph is going through. Your basic period is 2 pi, or 360 degrees. Your basic sine graph starts in the middle, or on the principal axis, then goes up, and then down, and then up. Your basic cosine graph starts high, which for your basic graph would be up at a y value of 1, goes down, and then back up. Tangent graph. Okay, we know that tan is the same as sine x over cos x. So tan is going to be undefined wherever cos x is 0, which means that pi over 2, at 3 pi over 2, etc. That means we get vertical asymptotes at x equals pi over 2, at x equals 3 pi over 2, and so on. If we kept on going to the left, we'd have one at x equals negative pi over 2. All those places that cos x is 0. The graph of tan x is periodic, but it's only got a period of pi, so it's half as big as the period of sine and cosine. So what does that mean if we want to model with sine and cosine graphs? Well, there are different parameters we can use to change what these graphs look like. We can stretch them, we can translate them, we can reflect them. So I've given these basic forms of y equals a sine b x minus c plus d, and same thing with cosine. The letters that I chose are completely arbitrary, so the IB may use different letters, or they might use the same ones on a given question. What do each of these letters do? Well, first of all, the a value controls the amplitude. Really, absolute value of a is amplitude. We only talk in terms of positive numbers for the amplitude. It can be found by taking the difference between the max and min, then dividing by 2. It also controls reflections through the x-axis, just like if you have a function that's got a negative in front of it, you're talking about an x-axis reflection. Some of our basic properties of functions or function rules that we looked at in topic 2. This is going to hold true for a sine graph. So there's the start of y equals sine x. If instead I wanted to graph y equals negative sine x, that's going to produce an x-axis reflection. So everything that was above is now below and vice versa. The b value controls the period, but it isn't the period. If b is 1, then you have a default period of 2 pi. Okay? So we can say that generally the period of a graph is 2 pi over b. And that would give us a period of 2 pi if you put in 1 for b. And if you're looking for what the b value is and you know the period, this can just be rearranged and solved for b so that you get b equals 2 pi over the period. The c value, okay, it's in with the x. We know that that controls our translation to the left and right, or horizontal translation, sometimes called phase shift when we're talking about these periodic graphs. So the graph of y equals cos x minus pi over 4 will be a cosine graph that shifted pi over 4 units. And since it's minus pi over 4, we're going to the right. If it had been plus, we'd be going to the left. So instead of having this as my basic starting point, up to 2 pi, now I'm going to be starting pi over 4 over. Now starting is a relative term here, because these graphs continue forever and ever in both directions. So this would be my y equals cos x minus pi over 4. And our top position, our max, would occur at pi over 4, and then at 2 1/4 pi over 4, or 9 pi over 4. Okay? But again, keeps going forever and ever in both directions. The graph of y equals sine x plus pi. That's going to be a sine graph that shifted pi units. And since it's a plus pi, we're moving it to the left. Okay, so the original y equals sine x graph looks like this. That's a little too rough a sketch. Now I'm going to move it over pi units. So this was 2 pi. Now it's going to be moved over here. Okay, everything gets shifted over pi units. And it looks like this. Notice how sometimes it's tough to tell exactly what transformation's been performed, because different transformations can lead to the exact same graph. What I graphed here of y equals sine x plus pi would be the same as flipping my original blue graph in the x-axis. D value controls the vertical shift and the location of the principal axis, and the principal axis is just that horizontal line that moves through the middle of a sine or cosine graph. In the default graph, it's the x-axis, or the line y equals 0. It's halfway between the max and min values of the graph. So if you want to find the d value, it's really just the average of your max and min. All right, let's put this to use here. The graph of f at x equals p cos q x minus r plus s. This has got all the different parts to it. So we're going to have to find amplitude, period, use period, find a horizontal shift and a vertical shift. It's shown below for the domain 0 to 10. Okay, let's look at what we know. We've got a max at 3, 2, and we've got a min at 7, negative 8. We want to find the amplitude of this function. So we said it was the difference between max and min divided by 2. So for us, we've got a max of 2, a min of negative 8, divided by 2 equals 5. Another way to think of it is there are 10 units in between the top and bottom. Divide that by 2, and you get 5 for your amplitude. All right, Q has something to do with the period. Now let's see here. We had an x value of 3 at a max. We had an x value of 7 at our min. That's not a full cycle, though. That's only half a cycle. So we'd expect to need another 4 units to finish off the cycle. And we could expect another max up here at 11.2. Meaning that we have a period of 8. So half a period was 4 units. Our Q is the same as what I called B on the last slide. It's going to be 2 pi over that number, or simplified pi over 4. Okay, this is a cosine graph. Cosine graphs start high generally. So this starts high, and it's starting at an x value of 3. Regularly, a cosine graph should start high at an x value of 0. Okay, this would be our basic cosine graph. Would start up here, and then is going to move like this. This has been shifted over to the right then. So it's been shifted right 3 units, or translated right 3 units. So our R value must be 3. Finally, principal axis. Occurs at y equals the average of your max and min. Okay, so for us, that would be 2 plus negative 8 all over 2, be negative 6 over 2, or negative 3. Meaning that really what we have now is an equation that says y equals 5 cos pi over 4 x minus 3, close brackets again, minus 3. I wonder if that will actually give us something that looks like our graph over here. Let's double check with the GDC. And on a paper 2, you always can actually double check these. 5 cos pi over 4 of x minus 3, close brackets, minus 3. I'll set some window settings that look similar to what we had before. So 0 to 10 for my x's. Y's are going to a min of negative 10 and to a max of 5. Doesn't look too good. So if this were your paper 2, you wouldn't want to freak out at this point. You'd want to troubleshoot. I wonder if I'm in degree or radian mode. There's the problem. Ooh, that looks very similar to what we have in our picture. All right, hence find all solutions to the equation f at x equals negative 6. Let's assume that this is going to be a paper 2 question. So I would put in f at x in my y1, negative 6 in my y2, and look for their points of intersection. Luckily, I've already done the graph. Points of intersection. So there's definitely a point of intersection at x equals 5.82. And you might want to sketch a little graph to show your method. Looks like there's another point of intersection. Second curve, I'll have to go over closer to it. 8.18. Now, you might want to zoom in and figure out whether there's one last one. It looks like there might be over to the left. First curve, second curve, somewhere around 0. And indeed, there's a point of intersection at 0.18. We could have also reasoned that out because there's a point of intersection at 8.18, and that should occur periodically every 8 units. Oh, they love these types of questions. The equation f at x equals k has exactly one solution. Write down the two possible values of k. So think about what we just did in that question where we were solving graphically. We found 3 points of intersection for where we had -6 for our y value. Think of all the different equations you could set up here, and you'd have basically a vertical, or rather a horizontal line that you're passing through the graph. So right here, I'm going to have 3 solutions, 3 solutions, 3 solutions, 3 solutions, 2, 2, 2, 2, ding, ding, ding. There's one solution where y is -8. Wonder if that occurs anywhere else. 3 solutions, 3 solutions, 3 solutions, 3 solutions, 2 solutions, 2 solutions, 1 that also occurs where y has a value of 2. So the two possible k values that get exactly one solution are k equals -8 and k equals 2. They're really asking you, do you understand the concept of a graphical solution here? All right, trig equations. Working knowledge of trig ratios from 0 to 360 is required. If you know the values of the table on page 1, then the unit circle should be pretty straightforward. Okay, so let's solve this one. 2 sine of x over 4 equals root 3 for 0 to 10 pi. What I want to do here is isolate my trigonometric term, or my trig ratio, and I get root 3 over 2. That sounds familiar. I know that there were places where I had a sine of root 3 over 2. It happened at 60 degrees, okay, which would be pi over 3 radians. But I should also have another place in my unit circle where that happens. I've got the same y value, or the same sine, over here at what should be 60 degrees from the x-axis on the other side, which would mean in total 120 degrees, or 2 pi over 3. So if you know the unit circle really well, or if you can draw it quickly, you probably don't need to do all this reasoning out from the x-axis, but this is one way that I like to do it. So it seems like there are two angles that work here. For sine x over 4, or to have a sine of root 3 over 2, you can have an angle of pi over 3, or you can have an angle of 2 pi over 3. But we should realize that this is periodic around 2 pi. Sine values recur every 360 degrees, or 2 pi units, so my general solution is going to have a plus 2 k pi, where k is going to be some kind of integer. Okay, if we solve this, let's just times both sides by 4. We get 4 pi over 3 plus 8k pi. And this would give us x equals 8 pi over 3 plus 8k pi. Looking carefully at the domain, I think about which of my solutions are going to work. So obviously 4 pi over 3 is going to work. Also 8 pi over 3. Now I can put different values in, different integer values in for k, and see if it works in my domain. So say I put in 1 for k here. This would be 4 pi over 3 plus 8 pi. Or, in other words, 28 pi over 3. That's still okay. That's still between 0 and 10 pi. If I put in 1 for k here, I'm going to get 8 pi over 3 plus 8 pi, or 32 pi over 3. That is outside of my domain here. So now our values are getting too big. If I put in negative values for k, it's going to be too small. On the left-hand side, it's going to be smaller than 0. So this would be our full solution set with the given domain. These here would be our general solutions, and that should be 8k. Some people use n. The choice of letters, again, arbitrary, doesn't make any difference. Sometimes you can end up with questions where you've got a combination of trig equations and quadratic equations. So this one here should raise some alarm bells. We've got a 2 sine squared. Looks like a quadratic. And in quadratics, generally, you want to make one side 0. So let's do that. Now think about if you had had 2n squared minus n minus 1 equals 0. You'd know that you'd need to factor this, and you could figure out how to factor it. Okay, this will be a minus 1 and a plus 1. By the same token, you can factor this expression over here. It would become 2 sine x and a sine x, because the only way to times to sine squared would be a sine x times a sine x. All right, and we'd have our minus 1 over here, and we'd have our plus 1 over here. This gives us a mini equation, 2 sine x plus 1 equals 0, or 2 sine x equals negative 1. Sine x is negative 1/2. Okay. Think where that occurs. And for me, I'd be thinking about sine x is 1/2 at 30 degrees. And I have negative signs right here and right here. So this would be 30 degrees and 30 degrees. Or if I went for my angle in standard position, 210 degrees, 7 pi over 6. And then 330 degrees, or 11 pi over 6. So those must be the angles we're talking about. X equals 7 pi over 6 and 11 pi over 6. Since my domain's restricted here to 2 pi, I don't really have to take a look at the general solution, though it would be nice if I did. Sine x minus 1 equals 0 means sine x equals 1. Okay, and there's only one place where that occurs between 0 and 2 pi. That's right here at 90 degrees, or pi over 2. So these would all be solutions. I had to factor, get my 2 elementary equations, and find the corresponding angles for each of their scenarios. Okay, you have a bunch of trig identities that appear in your formula booklet, and they can be rearranged. So we talked about how tan theta is the same as sine theta over cos theta. We have this lovely and romantic one here. If I were sine squared theta and you were cosine squared theta, together we'd be 1. Oh, isn't that a beautiful sentiment? Double angle formulae. Okay, we've got sine 2 theta equals 2 sine theta cos theta. You can just read these. And then different versions for cos of 2 theta. So you can turn it into this one, or by combining it with this up here, turn it into this or this. Don't necessarily need to be memorized, but you do need to make sure you can find it quickly in your formula booklet. Okay, tangent equations. So if I had tangent of x minus pi over 4 equals root 3, I'd say to myself, and it's solving for all x, so the general solution. I have to ask myself, where do I have a tangent of root 3? Well, the first place it occurs is going to be at 60 degrees, or pi over 3 radians. That means x minus pi over 4 is pi over 3, plus k pi in this case. Okay. Because tangent functions are periodic with a period of just pi. Now I can add pi over 4 to both sides, and I'd get 7 pi over 12 plus k pi, where k is an integer. So that's going to give me all the different possible solutions to this at 7 pi over 12, at 19 pi over 12, and so on. All right, sometimes they like to put them together so that you've got a sine and a cosine in the same question. Generally, if you see sine and cosine and that's it in the question, you can rearrange this so that you get it as a tangent equation. So I could move my cosine over here. And if I divided both sides by cos x, I'd have sine over cosine, which is just tangent. Equals negative root 3. Tan x equals negative root 3 over 3. Okay. Where does that occur? Well, I know root 3 over 3 occurs at 30 degrees. I'm thinking all are positive here, only sine is positive here, only tangent's positive here, only cosine's positive here. So I'm going to have this reference angle of 30 degrees in my second quadrant, which would be 5 pi over 6 as my angle in standard position for that. And I'm also going to have a reference angle of 30 degrees over here, and we'd be talking about 11 pi over 6. Alternately, I could have just looked at the general solution using that first one. So I could say x equals 5 pi over 6 plus k pi. Okay. For this given domain, that would give me solutions of 5 pi over 6. And the same thing plus another pi, or 11 pi over 6. So either straight from these two places in the unit circle, or the general solution, and just making sure I've considered all cases within the domain. Last one. Here's where it gets pretty fun, and I think this one is actually from an old IB exam. So we've got cos 2x minus 3 cos x minus 3 minus cos squared x equals sine squared x. Solve this from 0 to 2 pi. Wow. Okay, the only thing I really notice here is that cos x is probably going to have to make an appearance somewhere. Everything else I could rewrite in another way. So cos squared, I could use one of my identities. Cos 2x, I can use one of my identities. But the cos x is going to have to stay. Let's see if I can express this all in terms of cosines. So I can turn cos 2x into 2 cos squared x minus 1. Let's do that. Then I'd have my minus 3 cos x minus 3. Oh, there might be something slick I can do over here. Looks like this will be quadratic anyway, so I might as well make one side 0. Okay. There are a lot of ways that you can deal with this sine squared on the other side. I kind of like this way because I end up with 2 cos squared x minus 1 minus 3 cos x minus 3 minus, if I factor out the negative from these two, I get cos squared x plus sine squared x. Oh, and we know that that's 1. So rewrite minus 1 minus 3 cos x minus 3 minus 1 equals 0. Alternately, right from the start, you could have turned this sine squared into 1 minus cos squared x. All right, that gives us 2 cos squared x minus 3 cos x minus 5 equals 0. Again, it's a quadratic. Let's factor it. We're going to have a 2 cos x and a cos x. We've got a prime number on the end. That's a gift. So either the 5 goes here and the 1 goes here. Let's see, is that going to work out for us? Oh, yes, it is. If we make this one positive and this one negative, If I FOIL that out or use the distributive property, I'll get 2 cos squared x minus 3 cos x minus 5. Each of those has to yield an elementary equation. So I get 2 cos x minus 5 equals 0, or 2 cos x equals 5, or cos x equals 5 over 2. You should know that this is impossible. You can't have cosine values that are greater than 1. You can justify that from the graph. You can justify it from the meaning of cosine being adjacent over hypotenuse. You can't have the bigger number on top. Okay, so this yields absolutely no solutions. Then we'd have cos x plus 1 equals 0, or cos x is negative 1. If you think of your unit circles as your x values being your cosine, your y's being your sines, cos x is negative 1 at 180 degrees or at pi. Don't have to look at the general solution here because I'm limited from 0 to 2 pi. All right, so that's a fair bit to go through in a fairly short amount of time. You may want to brush up on some of this stuff outside of this video, but hopefully that's sort of got you at least thinking about your trig material. Tune in for another review.